How do quantum error correction codes beat quantum noise? Imagine trying to keep a delicate soap bubble intact in a gusty wind. That's similar to what quantum computers face with quantum noise. It's a constant challenge because qubits are so sensitive. But scientists have developed clever ways to protect quantum information. They use quantum error correction codes to do this. These codes work by spreading the information across many physical qubits, creating what's called a logical qubit. This logical qubit can detect and fix errors without directly measuring the quantum information itself. Why is that important? Because measuring a qubit directly can destroy its quantum state. So, these codes use indirect measurements called syndrome measurements. These reveal error patterns without collapsing the quantum state. Once errors are identified, the system applies corrective operations to restore the original state. There are two main types of errors that these codes target. One is called a bit flip error, where a qubit state flips from 0 to 1 or vice versa. The other is a phase flip error, which changes the relative phase between quantum states. Both types can mess up calculations if not corrected. To handle these, quantum error correction codes spread the information over multiple qubits arranged in specific patterns. One popular approach is the surface code, which arranges qubits in a two-dimensional grid. When more physical qubits are added, the chance of errors slipping through drops exponentially. But this only works if the physical qubits are not too noisy. If they are too noisy, adding more can actually make errors worse. Recent advances have introduced new types of quantum codes that need fewer physical qubits per logical qubit. Some of these codes can detect errors in a single shot, speeding up the correction process. These improvements can cut error rates by large factors, sometimes 1,000 times lower than before. That means quantum computers can run longer and more reliably. Practical experiments have shown that logical qubits, protected by these codes, last longer and have fewer errors than their physical counterparts. Fast decoding algorithms interpret error signals in microseconds, allowing corrections to happen in real time. In essence, quantum error correction codes beat quantum noise by cleverly encoding information across many qubits, detecting errors without destroying the quantum state, and fixing errors quickly. This process keeps the fragile quantum information safe, making reliable quantum computing possible despite the noisy environment.